Welcome friends. So in today's topic we are going to learn how to find the elongation in the bar due to its self weight. So let's see. In this we have two possible cases. The first case is when the bar has uniform area of cross section. Now let me show you the case. So if you look at here, so we have got a bar over here. So bar is hanging vertically with the fixed support, and on account of its weight there will be elongation in the bar. So there shall be some elongation in the bar due to its weight. Let's say we have got L is the original length of the bar, and this much portion which I have shown dotted is the elongation in the bar. I'm going to call it as delta L due to its self weight. A is the area of cross section, and then area of cross section is uniform throughout. So due to its own weight, it is going to undergo the elongation. So we have to find out the elongation due to its own weight when it is hanged vertically with the fixed support. Now if you look at a standard case, we are considering a bar whose weight is negligible, and if this bar is being pulled axially by a load P, so there will be an elongation delta L in the bar. Okay, if the area of cross section of the bar is A, so the elongation of the bar is given by an expression delta L equals the axial load times original length divided by area of cross section times the modulus of elasticity. So this is the standard case when a bar is subjected to the axial load and we have considered the weight of the bar as negligible. So in that case, the elongation in the bar is given as PL by AE. That is a conventional case. Okay, but here if you see, here there is nothing like the axial load applied from outside. So this particular bar is getting deformation due to its own weight. So weight is acting on the bar actually, and it is going to create the elongation in the bar, and that elongation is delta L. So in order to apply the standard situation over here, I have considered this much portion of the bar having length x. This much portion of the bar is going to have some weight, and that is going to act downward. Now just above this portion of the bar, I am considering a small element having very small thickness. I am considering a small element of the bar like this. So I have considered a small element of the bar. This small element of the bar is having small length dx. So now you can see in this situation, the weight of the bar having length x is going to apply axial load on this small element that is having length dx. So this small element dx is getting deformed due to the weight of the x length of the bar. So considering a small length dx of the bar supporting the weight of the bar having length x, as it is clear from this picture. So this small length of the bar will undergo deformation. So I can assume the small length of the bar as weightless, and it is being pulled by a weight of the bar having length x. Okay, so I am calling the weight of the bar as capital W suffix x. Okay, so now I can apply the standard condition for this small length of the bar. So let Wx equals the weight of the bar of length x. Right. Therefore, now if I want to find weight of the bar having length x, this can be written as that weight density of the material. So let me call weight density as small w times the volume of the bar having length x. So that will be simplified as, so weight of the bar having length x is given by weight density, which is w we got, times, now volume of the bar having length is area of cross section into height. The area of cross section is A, and the height is, as we know, height is x. So height is nothing but length. Okay, so you can see the weight of the bar having length x is W into A into x. Now by following the standard case for the small element, therefore deformation in the small element having length x. So the small element what we have considered is having very small length, that is dx, having length dx. So the original length of the element is dx, so deformation I am going to call as delta. So deformation, that is delta in the length, and the original length is dx. So delta in the length dx is nothing but the same conventional formula we have to use. P is the load, so here load is Wx into length, the original length of the bar small element is dx, divided by area of cross section. Area of cross section is A times modulus of elasticity. We have considered the area of cross section as same throughout. So we are assuming that the deformation, overall deformation is going to be very small, so variation of area is not so much significant. So I am neglecting the variation of area due to deformation in that particular case. So if you see here, it is going to be Wx is nothing but the weight density times area of cross section times x, and then we have dx whole divided by again area of cross section times modulus of velocity E. This is the deformation in the small element we have considered. Now if I want to find overall deformation, so I will have to consider this kind of small disc starting from bottom up to the end. Okay, I can start like this. So in that case, if I want to find overall deformation, then similar small disc I will have to take from the bottom, from here. So I should take disc like this, then I should take another disc over here, and I should find deformation in the disc. Then I should take another disc over it, and I should find deformation in that disc also, right? So subsequently, if I keep on selecting swing elements like this from top to bottom, we will add all this deformation starting from bottom to the top. When you start from the bottom, at this point your x is going to be 0. X is going to be 0, and then you continue the same procedure till top where your x is going to be L. So you are going to start from x equal to 0 to x equal to L, and you are going to find out deformation in the thin disc from bottom till top onwards, right? So that procedure of finding out small deformation in thin discs or thin elements, right, is called as integration. So if you integrate this particular deformation from x equal to 0 to x equal to L, right, you will be able to find out the overall deformation due to self weight. So therefore the total elongation in bar due to self weight is given as, so the total elongation due to self weight is given by integrating small elongation in the thin elements. Okay, and that is total elongation I have considered as delta L. So delta L is given as integration of small elongations, that is delta dx starting from x equal to 0 to x equal to L at the topmost point. So now I'll substitute the corresponding values. If you see here, the weight density, that is weight per unit volume, is constant, area is again constant, E is again constant, so only x dx will remain inside. So you'll get W. If you want, you can cancel area in numerator and denominator. You'll get W, that is weight density, divided by E, and then in integration you will have limit 0 to L and x dx. So x dx is simple integration, x square by 2. You'll have weight density divided by E times x square by 2 starting from 0 to L, and therefore if I further simplify this, this is going to be 1 upon 2 weight density by E into L square, because if I put the limit, the upper limit is L, so it is L square by 2 minus 0 square by 2, so it is half W by E L square. Right, now there is a small modification we can do, that we can divide and multiply numerator and denominator by area, because area is required here. So you'll get, from here you'll get delta L equals half times, now you'll have weight density into area of cross section into L into L. I have broken L into L, and then divide by again area of cross section times E. Now if you look at this particular term, that is W into A into L. W is weight density, this area into L, this particular portion is area into L portion is nothing but area into L is a volume, so it is going to be volume. So weight density into volume of entire bar, so that is going to be the entire weight of the bar. So it is nothing but W, that is entire weight of the bar, into L by AE, right? Because area of cross section into L is the volume of the bar. So you will get from here that overall elongation is nothing but half times, so weight density into volume of the bar is nothing but the weight of the bar, so I'll say W, overall weight of the bar, times length of the bar L divided by area of cross section times Young's modulus, right? So here W is the weight, total weight of the bar, right? Here note W is total weight of the bar. This way you can find out the elongation in the bar having uniform area of cross section A and weight W, length L, and modulus of velocity is E. So this way you can find out the overall elongation in the length of the bar due to its own weight. Okay, so we would like to solve this problem to understand the concept of deformation or elongation in the bar due to self weight. So let me read the problem for you. So we have got a steel rod of diameter 8 centimeters and length 10 meters, and it is connected vertically at one of its end with fixed support, and the density of steel is 8000 kg per meter cube and the modulus of elasticity is 205 gigapascal. We have determined the elongation of the wire. So it is very straightforward problem. We have to find the elongation of the wire due to self weight, because here there is no other external load is acting on the bar, only its weight is going to be acting. So if you look at here, we have got a steel bar. So we have got the length of the bar as 10 meters. That is fine. L equal to 10 meters. Length is given as 10 meters here, and we have diameter D equals 8 centimeters. So we'll try to convert that centimeter into meter. It is 0.08 meter. Okay. Now next is they have given us density. Density is they have given as mass density over here. So that is rho. Rho is 8000 kgs per meter cube. From here we can find out the weight density. So weight density, that is small w, is going to be mass density times gravitational acceleration. So that is going to be 8000 times 9.81 newtons per meter cube. Since we have followed weight density, now like in our expressions, so we shall be using weight density here also. So we have got weight density here, and then they have given modulus of elasticity. So the modulus of elasticity they have given as, that is Young's modulus, is 205 GPa, gigapascal. So that is going to be 205 into 10 raised to newtons per meter square. So I am following here all SI units. So we can change the unit according to our requirements. So here everything is easy to, we can easily convert all data into SI units. So I have converted everything into SI unit. Fine. We need to find the elongation of the wire in this situation. So we know that for uniform area bar, the elongation, that is delta L, is given by, so it is actual weight into original length divided by 2 times area of cross sections times Young's modulus. This is how we find. So the expression of elongation due to self weight, that is delta L, is nothing but is the total weight of the bar, self weight, times L divided by 2 times area of cross section times Young's modulus. This is the expression we have already derived. So now if I want to find weight here, so weight is going to be weight density into volume. Volume is nothing but area of cross section times length. So this is nothing but overall weight density into, and then times L divided by 2 times area of cross section times Young's modulus. Now we have simplified the whole expression. We can put the corresponding values. Here we can cancel area of cross section from numerator and denominator. So now what is remaining is weight density is 8000 into 9.81 into L square. Original length is given as 10 meters. 10 meters square divided by 2 into the modulus of elasticity is 205 into. You can see here in this particular expression, the diameter is not important. The only important factor over here is the length, right? So same expression if you write here, which is deformation in the length. So if you simplify this WL by 2AE, so remaining expression would have only weight density, length square divided by 2E. So we can conclude from here that the elongation in the bar is mainly dependent on the original length. If length is high, even though area of cross section is less, but if the length is more, then it is undergoing more elongation. Okay, this is very important portion to be understood. So here diameter is not significant as far as overall deformation is concerned. Put any diameter, keep the same length, you will get same elongation. So this is what you are going to get. So the deformation after calculation you will get 0.019. Okay, similarly we can take one more example to understand. So let me show you the next example. So we have got a steel wire of diameter 8 mm and the length of the wire is 100 meter, it is connected vertically at its top end with the fixed support, and a load of 1.5 kilonewton is attached to the bottom end. If the density of the steel is 8000 kg per meter cube and the modulus of velocity is 205 gigapascal, determine the elongation of the wire. So if you read here carefully, there is an external load attached, the load of 1.5 kilonewton attached, and as well as we have got a huge length of the wire, that is 100-meter length of the wire. So in this situation, we cannot neglect the elongation due to its self weight, because there is a 100-meter length involved. So here we have to consider elongation due to self weight as well as due to external load. This is an important point here to note. Now let me draw the schematic diagram just to make it more clear. So we have a bar, and this bar is also subjected to some external load. This is, I'm going to call external load P. This external load P would cause a deformation in the member as well as its self weight. They have given us, there's a length around 100 meter of the wire. The diameter is also given as 8 mm. This is a very important point to remember here, that we are going to consider the elongation due to self weight as well as due to external load. So let me write down the data available with us. That is, diameter is given to us D, which is 8 mm. So we can convert into SI unit. So it is going to be 8 into 10 raised to minus 3 meters. Then also we have here the original length, that is 100 meters, and external load, value of external load is 1.5 kilonewton, 5 kilonewton. So it is 1.5 kilonewton, that is 1.5 into 10 raised to 3 newtons. We also have got mass density rho, 8000 kg per meter cube. This will give us the weight density, small w, that is mass density times gravitational acceleration. This is 8000 multiplied by 9.81 newtons per meter cube. We also have got the modulus of velocity, that is Young's modulus, and that is nothing but 205 gigapascal. That's nothing but 205 into 10 raised to 9 giga newtons per meter square. Pascal is newton per meter. So we have got all the data available with us. So now, as we know that the total elongation is due to self weight as well as external load. So I'll first write down the elongation due to self weight. I'm going to call delta L1, and that is nothing but, 1 upon 2 times the overall weight into overall length divided by area of cross section times E. This we have already derived earlier. This can be further simplified as 1 upon 2. Overall weight is weight density into volume. Volume is area of cross section times overall length, and then times overall length divided by area times E. So if you see here, this A and this A get cancelled out. So you will be getting a simplified expression of delta L1 elongation due to self weight as, you can remember this directly. So it is W L square divided by 2E from here. So let me substitute the values. So W is weight density, which is 8000 into 9.81. L is 100 meters, so it is 100 square divided by 2 into E is 205 into 10 raised to 9. So if you solve this, you will be getting the elongation due to self weight. So that value is going to be 1.914 into 10 raised to 3 minus 3 meters. So we got the value of delta L, that is elongation due to self weight. Now next we'll have elongation due to external load. So let's do it. That I'm calling as delta L2. It is nothing but load into length, area into, so let us put up the values. So load is external load, they have given as external load, they have given 1.5 in 10 raised to 3, okay, newtons. Original length is 100 meters, divided by area of cross section is pi by 4 d square, d is into E is 205 into 10 raised to 9. This value will be 0.0145 meters. So therefore, the total elongation would be the sum of elongation due to self weight and the elongation due to external applied load. So we can find out the total elongation as delta L1 plus delta L2. That is the summation of these two values. So this will turn out to be around 1.914 mm, and this value will be around 14.5 mm. So if you add both of them together, you will get around 14 and 2, around you'll get 16.48 mm, approximately 16.5 mm we can say.